everyone. In this video, we're going to continue our discussion on mass spectrometry, and I'm going to give you a few more tools that you can use to identify an unknown compound. So previously we talked about the parent peak for our compound, and we also talked about the M+1 peak, which is due to the carbon-13 isotope. Now, if you have a chlorine or a bromine in your molecule, then you'll actually see an M+2 peak. So if you do see an M+2 peak, that indicates that you have chlorine or bromine in your original compound. So why is that? Well, let's look at the most abundant isotopes for chlorine and bromine. So for chlorine, we have chlorine 35 and chlorine 37. And if we look at their abundance values, chlorine 35 is 75.78% abundant. Chlorine 37 has an abundance of 24.22%. Now, if we look at the ratio of those two, it's about 3 to 1. So let's look at figure 15.26 below, and you can see our compound has a chlorine in it. Now, if we go to the rightmost cluster of peaks, we see our parent peak, and that is due to chlorine 35. And then we also see an M+2 peak, and that is due to chlorine 37. And you'll notice that the ratio of those peaks is about 3 to 1. So if you see two peaks in your rightmost cluster, and they're about 3 to 1 in terms of ratio, then that means that you have chlorine in your original molecule. Now, there is still an M+1 peak kind of hiding down below, and again, remember that's due to carbon-13. Okay, so what about bromine? Well, the two most abundant isotopes for bromine are bromine 79 and bromine 81. So let's look at the natural abundance of each. So the natural abundance of bromine 79 is 50.69%, and the natural abundance of bromine 81 is 49.31%. So they're approximately equal to each other, so we would see a 1-to-1 ratio. And if we look at figure 15.27 down below, our molecule has bromine in it. And if we go to the rightmost cluster, we see our parent peak, and that is due to bromine 79. And then 2 over from that is our M+2 peak, and that's due to bromine 81. So, additionally, those peaks are an approximately 1-to-1 ratio. So if you look at your rightmost cluster and you notice two peaks that are approximately the same height, and they're 2 apart from each other, then that is likely due to a bromine in your molecule. So yet another tool we have. Now, let's also talk about fragments that can occur in your molecule. So remember, when a molecule enters a mass spectrometer, it's ionized. So it's hit by a beam of electrons, and that can result in fragmentation. So maybe a methyl group leaves, maybe an ethyl group leaves, etc. And this particular diagram shows a lot of different possible fragments that can occur in mass spectrometry. So these are some of the more possible or common fragments that could occur. So most of the time what you'll notice is a peak that is below your parent peak. So for instance, your parent peak, let's say, is 40. If you lose a mass of 15 from your parent peak, which is the same mass as your original compound, you'll find a peak at about 25. So that 15 indicates that we lost a methyl group. If you lose a mass of 29, that indicates an ethyl group. And we could keep going. So if you lose a mass of 43, that indicates a carbonyl group with a methyl group attached. Let's see, a mass of 77 indicates a benzene ring. So there's a lot of different possible fragments that can occur in mass spectrometry. And we'll go over an example later on where we try to kind of figure out what the structure of our molecule is based on the fragments that were lost. But let's make a list of possible fragments or more common fragments. So if you're looking at your mass spectrum and you find your parent peak, and let's say you have another peak that's 15 m over z lower than that, again, that means that you have a loss of a methyl group. So again, let's say we have our mass spectrum. Let's say this is our parent peak. If you find a peak 15 below that, so the difference is 15, then that is due to the loss of a methyl group. So maybe you have this compound and you lost your methyl group off of the end. All right. Okay, so now let's see some other common fragments. You could also lose an ethyl group, which has a mass of 29. So that means if you start at your parent peak and you have a peak that's 29 less than that, then you lost an ethyl group. M minus 43 would indicate loss of a propyl group, which would have 3 carbons. M minus 57 would indicate loss of a butyl group, which has 4 carbons. And you could keep going, but these are the most common losses. Another common loss is M minus 18. So that indicates a loss of water. And the most common molecule that you would lose water from is an alcohol. Okay, and then most of the losses that we've seen so far have an odd mass. So methyl has a mass of 15, ethyl has a mass of 29, etc. Now, if you lose a mass that has an even number, that actually indicates that you started with a ketone or an aldehyde. So we'll just write M minus X, where X is an even mass. And that indicates, not loss. But that indicates something called Mclafferty rearrangement. And this is a pretty common occurrence if you have a ketone or an aldehyde. And we'll talk about that in more detail in a bit. So common fragments are due to different factors. So they can be due to the strength of your bond. So weaker bonds will fragment more easily. Common fragments can also be due to resonance. So if you lose a fragment and the resulting product has a resonance structure, then that means it's more stable. So this is kind of similar to when we were talking about acids and bases. And after the loss of a proton, if the conjugate base was resonance stabilized, that meant that the original acid lost its proton really easily. So it's the same thing here. Let's say the loss of a methyl group resulted in a resonance stabilized compound. Then that means the loss of the methyl group is highly favorable. So let's see, we'll call this cation stabilization. Because remember, in mass spectrometry, everything is an ion. It's a cation. All right, and then the last factor that can affect fragmentation is hyperconjugation. So let's say you lose a methyl group and that results in a tertiary carbocation. That will be super stable, so that loss of a methyl group will be favorable. But let's say you lose a methyl group from your compound and it results in a primary carbocation. That would not be very favorable, so you probably wouldn't lose that methyl group. So just remember, tertiary carbocations are more stable, more stable than secondary, which are more stable than primary carbocations, etc. All right, so let's actually look at a few examples of fragmentation that can occur. So let's start with an alcohol. And let's say we shoot this into our mass spectrometer. And remember, the first thing that happens is the molecule passes through a beam of electrons. And that beam of electrons is going to remove an electron from our molecule. So on an alcohol, we would lose that electron from oxygen. Now, what's really interesting is now that we have a radical, we're actually going to form a double bond down below. And that's going to cause the bond between these two carbons here to cleave. So that's homolytic cleavage. So then we end up with a double bond to oxygen. Oh, and I apologize. Oxygen will actually be positively charged for both of these steps here. And then our other product is a radical. Now, remember, in order for the detector to pick up on a molecule, it has to have a charge. So the radical does not have a charge, so it will not be detected. However, the other product is charged, so it will be detected. Now, there is a resonance structure for our positively charged product. So the pi electrons can move up to oxygen. So we can share that positive charge with the carbon below. Now, this is a common fragmentation pathway because the radical loss results in a resonance stabilized cation. So it's super stable. Now let's talk about alcohols a little bit more because there's another loss that could occur from an alcohol. So you could lose a water molecule. So let's say we have this alcohol here. And again, we put this into our mass spectrometer and we shoot a beam of electrons at it. The oxygen again loses an electron. And in this case, what happens is the oxygen is going to form a bond with one of the hydrogens on the end of the molecule. Now, this has to be a specific distance away, so I'm going to label the carbons alpha, beta, and gamma. So the alpha carbon is bonded to the oxygen, and then we have our beta carbon next to that, and then the gamma carbon next to that. So what happens here is the single electron from oxygen, and again, I forgot my positive charge on oxygen, but that single electron is going to team up with one of the electrons in the covalent bond between hydrogen and the gamma carbon. The other electron from that covalent bond will go to the gamma carbon. Now, that's going to end up forming a water molecule, H2O. And remember, H2O is a good leaving group. So, the water molecule is going to leave, and notice I drew a double-headed arrow for the loss of water. And we'll end up with a radical cation. So we have a single electron on that gamma carbon. So that's our radical part. And then after water leaves the molecule, the alpha carbon is positively charged. So the radical cation is charged, which means that it will be detected. The other product is the water molecule, which is neutral, so it will not be detected. So you wouldn't see a peak at m over z equals 18, for instance. You would only see a peak 18 below the parent peak. All right. So now let's look at another common fragmentation that can occur, and this time we're going to look at an amine. So remember, amines have a nitrogen. So if an amine enters a mass spectrometer, oh, my pen stopped working. Let me just figure that out there. Okay. So if an amine enters a mass spectrometer and it passes through a beam of electrons, similarly, that nitrogen will lose an electron. So again, very similar to our alcohol situation. And again, we're going to see a double bond form, and we'll also see a homolytic cleavage across that same carbon-carbon bond. So our products we have, oh, I keep forgetting that positive charge on the oxygen and the nitrogen. So this again looks very similar to our alcohol from before. We have a very similar radical that forms. So remember, the radical will not be detected because it does not have a charge. But our positively charged product will be detected and there is a resonance structure. So the pi electrons can move up to nitrogen, and we can share that positive charge with the carbon down below. So again, we have a resonance stabilized cation. All right, so now let's talk about that Mclafferty rearrangement that I mentioned earlier. So if you start with an aldehyde or a ketone, let's see what happens. So let's just say we start with a carbonyl group, and that R group could either be a hydrogen if we have an aldehyde, it could be a CH3 group, maybe it's an ethyl group. You know, we could really have any group there. But the same type of rearrangement occurs. So, again, let's say this passes through our beam of electrons. The oxygen is going to lose one electron. And we still have our R group. And then I'm just going to draw the other carbons slightly differently. So I'm just rotating the last carbon downward. And the reason for that is our radical oxygen is going to form a bond with one of the hydrogens on the end of the molecule. Now, the other electron in our carbon-hydrogen bond will end up forming a pi bond, and that kind of starts a whole cascade of electron movement. So we are going to again see a homolytic cleavage occur, and this will cause our fragmentation. So our products here will be an alkene, and we'll also see a radical cation. Now, the radical cation does have a resonance structure, so that radical electron can move over and form a pi bond with one of the pi electrons down below. And then the other pi electron will go to oxygen. So the double bond is going to move up to those two carbon atoms. All right, so again, this is resonance stabilized, which is why fragmentation can easily occur. Okay, so now let's look at our molecule here. So the mass of this molecule we're looking at, we have the R group plus, let's see, we have 2 carbons, so that would be 24. We have an oxygen, which is 16. And a hydrogen, which is 1. So that equals R plus, let's see, we'd have 30, 51, I believe? No, wait, 30, 41. I added 10 too many. Okay, so the mass of this carbonyl group here is 41 plus whatever the R group is. All right. Oh, sorry, I'm missing a couple hydrogens. Oh, wait, I'll just edit that. Edit, 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 edit. All right, so let's figure out the mass of our product. So we have the R group, which could be hydrogen, methyl, ethyl, plus, let's see, we have 2 carbons, so that would be 24 12 plus 12. We have an oxygen, which is 16. And we have actually 3 hydrogens, 1 on the oxygen, and then there's 2 hydrogens on the end. So that's a total of 3. And I'm just kind of rounding the masses here. So let's see, 24 plus 16, that would give us 40. And then plus 3, that gives us a mass of 43. Okay, so 43 plus whatever the R group is. So if the R group is a hydrogen, then the total mass would be 44. So we would see a peak at 44. If the R group is a methyl group, that would be 43 plus 15. So that would give us an M over Z peak at, let's see, 58. If the R group is an ethyl group, that would be 43 plus 29. So the M over Z peak would be at 72. Okay, so you can see that all of these are even numbers, which is why if you have M minus an even number, then it's likely that you started with an aldehyde or a ketone. Okay, so let's use all of these tools that we now have, and let's go back to problem 3 that we were working on, where we were trying to identify the molecular formula of a compound. So remember, in a previous lecture, we were working on this skill builder exercise, and we were trying to figure out the molecular formula of an unknown compound. So we figured out that the molecular formula was C5H10O, and we also figured out that there was a double bond or a ring in the compound. And we figured that out using the hydrogen deficiency index. So let's draw out all of the possible molecules or structures for C5H10O with a ring or a double bond. So the only real ring structure we could have is this epoxide that I drew. Let's see, let's look at some other possibilities. We could have a ketone. That one's symmetrical, but we could have an asymmetrical ketone. Let's see, we might have an aldehyde. We might have a branched aldehyde. So maybe we have a methyl group coming off of one of the carbons. We could have a branched ketone as well. There's a couple of different branched ketones we could have. We could have, let's see, a slightly different branched aldehyde. We could also have an alcohol with an alkene. And I think that's about it for constitutional isomers for this molecule. Okay, so now let's try to figure out which structure is the correct structure, just using the mass spectrum. So remember, previously we said that the peak at 86 is the parent peak. And that's at 86. And then let's look at the next closest peak. So it looks like the next closest peak is at 71. So let's look at the difference between 86 and 71. What is the difference there? 15. Okay. All right. So that would mean that we lost a methyl group. Okay, so now let's look at this next peak down below that. That is at 58. So let's figure out what the difference is between that peak and our parent peak. So that's a difference of 28, which is close enough to an ethyl group. You're not always going to have exactly the right loss, but that's okay. So that's close enough to an ethyl group. Okay, let's see. Then let's look at our base peak. Our base peak is the tallest peak. So this will be the most common fragment that's lost. And this is at 43. And I can tell that looking at our list of peaks over here. But it's also at 100% for the relative abundance. And 43 would either tell me I have a propyl fragment, so a loss of 3 carbons, or it could also be due to a carbonyl group with a methyl attached there, just like we saw in the Mclafferty rearrangement. Okay, so let's try to rule out some of our possibilities down below using what we figured out. Okay, so we know that we'll have a loss of an ethyl group. So are there any molecules that would not be able to lose a methyl group, or sorry, an ethyl group? Well, our ring structure would not be able to lose any of those substituents. So we can rule that out. Let's see. We know we're going to lose an ethyl group. So looking at this molecule here, I only see methyl groups that could be cut off. And I don't see any ethyl groups that could be cut off. So this is probably not our molecule. Also, the one next to that, this one, there's really only methyl groups that could be lost, or a tert-butyl group. So I don't think that's our molecule either. Okay. And then looking at the other molecules, there are potentially some losses here. Okay. What about the alcohol? Remember, if we have an alcohol, we're expecting an M-18 peak. So do we have an M-18 peak? Let's see, so 86 minus 18, what would that equal? So let's see, 86 minus 18, 68, right? Yeah, I don't see anything at 68, so we probably don't have an alcohol. Okay, so we've narrowed this down quite a bit. Let's see. Now, we also said that we would lose potentially a propyl group. So are there any molecules that could not lose a propyl group? Well, this ketone here only has ethyl groups, so we can rule that out. This aldehyde down below can only lose methyls or a tert propyl. So I don't see a propyl group that we could lose. This one over here can only lose a methyl or an ethyl. If we chopped off the bond here, that would be a branched group. And we don't have any indication of that, so we can rule that out. Let's go back to our Mclafferty rearrangement. So we know we have a carbonyl group. If the R group on our carbonyl there is a hydrogen, we would expect a peak at 44. But looking at our mass spectrum, our base peak is at 43. Okay, so that doesn't really make sense. If our R group is a methyl group, we would expect a peak at 58. So let's go back. Okay, so we do have a peak at 58. If the R group is an ethyl group, we would have a peak at 72. So let's go look. We have a peak at 71, but not 72. So most likely, we have a carbonyl group where the R is a methyl group. So actually, that rules out aldehydes. Okay, and we did kind of narrow down our molecules to either a ketone or an aldehyde, but now we know for sure that it's not an aldehyde. So our product must be that ketone there. Okay, so this was a lot of work to kind of narrow down what type of compound we have, but it is possible with just a mass spectrum to figure out the structure of your molecule. Okay, now let's kind of summarize everything we talked about, so all of the different tools that we have. Okay, so these are our guidelines for interpreting mass spec data. All right, so first step, find the molecular weight. And remember, you can find the molecular weight using the parent peak. So find the parent peak. And remember, that's in the rightmost cluster, and it'll be the tallest peak in the rightmost cluster. Then you're going to look for the M+2 peak. If you do see an M+2 peak, that means you have chlorine or bromine in your molecule. If you do not see the M+2 peak, then you can rule out chlorine and bromine. Next, determine if the molecular weight of your molecule is odd or even. If it's odd, then you know you have an odd number of nitrogens. If it's even, then you either have a hydrogen or a hydrocarbon or an even number of nitrogens. So that was the nitrogen rule. Next, look at the M+1 peak and also look at the data to find the relative abundance of the M+1 peak. That can tell you the number of carbons. So remember, we had a whole equation for that. So you might want to go back and look at your notes to figure out the equation for the number of carbons. Next, you're going to try to figure out the molecular formula from what you already know. How many carbons do you have? How much do they weigh? And then what is the leftover mass? Typically, the leftover mass will be due to oxygen and hydrogen, unless you already figured out that you have chlorine or bromine or a nitrogen. Then you want to determine the hydrogen deficiency index, and that will tell you how many pi bonds and rings you have. Then draw the possible constitutional isomers. So you're going to make a list of possible compounds. And then you can look at the fragments. And you can rule out compounds and try to narrow down which one you have. All right, so on Canvas, I posted a worksheet so that you can gain more practice with mass spectra and see if you can identify a compound given its mass spectrum. So you'll have to figure out the molecular formula, and then you'll also want to try to rule out any possible functional groups or halogens or nitrogens, etc. And then try to figure out the structure. I posted a video under modules week 7, or you can find this under Panopto recordings, additional videos. And I'll go over a couple of the mass spectra with you if you need help getting started. Okay, so I'll end the video here, and in the next video we'll go over some different types of mass spectrometry, and we'll talk about some newer applications of mass spectrometry as well. I'll see you then.